Okay, now that we see how to calculate torque, we're going to see how to find a net torque in a situation where there are multiple torques acting on some object. So, our situation, we have a 4-meter long, 200 kilogram board is pivoted about its center of mass with a 50 kilogram mass placed on one end. How far from the opposite end must an 80 kilogram mass be placed in order to keep the board balanced? Okay. So first thing we're going to talk about is this phrase right here, center of mass, and we have discussed it before a long time ago. So the best description for this that you need is that this is if the average place all mass is located in an object. And in this case, when we talk about center of mass for these big extended objects, the reason we talk about it is because we pretend, even though it's not 100% true, we pretend that all the mass in that object is concentrated there. If we didn't, well, then we'd have to have little mass force vectors for every single part of the object. We don't want to do that. That sounds like way too much work. So we're going to pretend that all of the mass for that board, 200 kilogram board, is at the center of mass. That's why we use this little trick. So here's what we got. We have our board. Okay. Here's our board. Here is the center of mass of that board. We are told that it is, let's see here, it's pivoted about its center of mass. That means the pivot point, which I'm just going to show with this like a little triangle thing. Okay, kind of like what's that word called? Fulcrum, I think. Kind of like a fulcrum on a seesaw. It's all the, let's see, the board is pivoted about its center of mass, so it's balanced right there. Okay, and we know that a 50 kilogram mass is placed on one end. So I'm going to put this over here. Here is our 50 kilogram object. And we want to know where an 80 kilogram mass must be placed in order to keep the board balanced. So we don't know where it's going to go, but you can kind of pretty obviously figure out that it's not going to go on this side. If it went on this side, there'd be nothing to balance out over here, and the board would tip. We want to keep the board balanced. Another word for that is we want to keep the board in rotational equilibrium. We want to keep the board balanced. We want to keep it doing exactly what it's doing right now. So we want to know where an 80 kilogram mass can be placed. We're not sure. So we're looking for a location. Let's draw the forces that are acting on our system. Okay. First one, well, we have a board, a 200 kilogram board, so obviously the force of gravity is acting on that object. Okay, so there's a force from the center of mass. Force of gravity always acts from the center of mass of an object, so I'm just going to call this Fg. It's pivoted about its center of mass. Well, if it's pivoted, then that means that it must be being supported by something. And it's being supported by the pivot point, the fulcrum here, at this point. So at this point, the board is being supported, and that's really a normal force if you think about it. Something is supporting the board. Okay, it's not just floating there, something's got to be supporting it. Okay. So we have two forces so far, both acting right from the axis of rotation and the center of mass. Oh, actually, let's not do axis of rotation just yet. We also have a 50 kilogram object on this end. So that 50 kilogram object puts a force downward on our board. And I'm not just going to call this Fg. Since this is a second object or another object, I'm going to call this Fg1. Okay? The board is Fg. The board has a force of Fg on it. This 50 kilogram mass, we're going to call that Fg1. And the other mass, we're going to call this, wherever this happens to act, we're going to call this Fg2. Okay. That's actually our free body diagram. All right, I know it looks a little confusing, but you should be able to tell that there's an arrow going up for the normal force here, an arrow going down for the force of gravity from the board, an arrow going down for the force of gravity from object 1, the 50 kilogram object, and an arrow going down for the force of the second force, or FG2, the force from the 80 kilogram object. Well, we want to know where this one ends up. Once we draw our free body diagram, our extended free body diagram, where we're not just making things into dots, now comes the time to write the net torque equation. T net. And my suggestion for writing T net is just like you did for writing F net. You write F net, then you write all the forces, whether they're positive or negative forces, and then you write down equals the MA, or in this case equals I times alpha. So let's just go right to left on here. The first force, let's see here. The first force is FG1. Now, so we know that there's a torque from our first mass, or from, I guess we just call it object 1, T1. Now the trick to telling if this is positive or negative is, well, we really should set an axis of rotation at this point. Before we even write this, what we should do is set an axis of rotation. In this situation, what we're going to do is set the axis of rotation right at the pivot point. You actually don't have to, and you'll see that in another example, but in this case it makes most sense to do so. We're going to set the axis of rotation right at the center of mass, right where this is pivoted, okay? So, to figure out which direction the object should, whether the torque is going to be a positive torque or a negative torque, a counterclockwise torque or a clockwise torque, what I usually do is I take my pen or pencil and I put it right on my axis of rotation, and I pretend that I can take this force and I can drag it to make it in the direction of that force to make this object rotate. Okay? If just this force was making this object rotate, then look how my hand is kind of tracing along. I'm grabbing this force and I'm dragging it in that direction. This is the counterclockwise direction. So that means the torque from object number 1, from FG1, must be positive. Let's get our other torques written down. There are two other forces acting right from the axis of rotation. So we have torque from the normal force and just the torque from the board. But something is interesting about these torques. Both of them act from the axis of rotation. And what did we just see up here when a torque acts at the same spot as the axis of rotation? R is 0. So these torques don't actually give us anything. Those forces do not cause torques because they act from the axis of rotation. Our last torque that we have to put on here is the torque from the 80 kilogram mass, which is somewhere over on this side, we figured out. So if I take this and I kind of rotate this around like this, this is clockwise, right? If I were to grab this force and pretend I can pull it this way, like it's on a string or something, this is clockwise motion. This must be a negative torque, so minus the torque from number 2. I've accounted for all the forces. 2 of them do not end up producing torques, but 2 of them do. So I end my equation with I alpha. And this is even going to simplify a little bit easier. Let me make a little note here. Torque at, so this is what we just talked about. The torque being at the axis of rotation means these torques are 0. Okay. We want to keep the board balanced. We want to keep it doing exactly what it's doing. It's balanced right now. We want to keep it balanced. Well, think about it like this. If we had a situation in linear motion where we had an object that was at rest and we wanted to make it stay at rest, or it was moving with a constant velocity and wanted to keep it at a constant velocity, that meant the acceleration was 0. Same thing here. We have a board that's balanced. We want to keep it balanced. What that means is we don't want it to have an angular acceleration. We want that to be 0. So, a little note, if alpha equals 0, which by the way it will in many, many cases as you're studying torque, not always, but a lot of them, then that means the system is balanced. Essentially, no change in the spin rate, I guess I would say, or the rotation rate. And no angular acceleration, obviously. which means F net, or torque net, T net, tau net, I should say, is 0 Newton meters. Okay? Now, all that's left is to set these torques equal to one another. T1 and T2, meaning the torque from this object, the torque from this object. Because this is 0 and these are 0, I can just pop this over to the other side, and I get T1, tau 1 equals tau 2. I'm going to move this up for you guys. There we go. Okay. Each of these torques can be calculated by using RF sine theta. So what I'm going to do is for each one, I'm going to write down R1, F1, sine theta 1 equals R2, F2, sine theta 2. Let's start with the sine thetas. The forces on each of these objects are pointing straight down. And at this point, the vector from the axis of rotation out to where these objects are acting is to the left and to the right. So you've got something down, or the force is down, R is out to the left. That's a 90-degree angle. Therefore, sine of 90 degrees is 1. Same thing over here. R, the R vector, would go from the axis of rotation to where the force is acting. It's to the right. The force is acting down. That's a 90-degree angle. This is 1. So we're left with R F1 equals R, or R1 F1 equals R2 F2. At this point, we probably should say that F1 is equal to M1G and F2 is equal to M2G. So I could rewrite this as R1 M1G equals R2 M2G. Notice what I have on both sides of my equation. I have G's. They'll cancel out. What I'm left with now is R1 M1 equals R2 M2. R1 is the displacement from the axis of rotation to where object 1 is acting, where that force is acting. The board is 4 meters long. Object 1 is at one end of the board. The board is pivoted about the middle. Axis of rotation is right in the middle. That means if this whole thing is 4 meters long, this has just got to be 2 meters. So R1 must be 2. M1 is the mass of object 1 causing this rotation, 50 kilograms. R2 is what we're looking for, isn't it? It's how far from the axis of rotation this object is. So we can find that pretty easily because we know what M2 is. M2 is 80 kilograms. So if I were to solve this, I would get 100 equals 80 times R2. I divide both sides by 80. I do 100 divided by 80, and I get 1.25. Now, what does that mean? What this says, the question asks, how far from the opposite end must an 80 kilogram mass be placed in order to keep the board balanced? What I just found was R2 equals 1.25 meters. Remember what R2 means? That's the displacement from the axis of rotation. That's got to be 1.25 meters from our axis of rotation to here. Okay? This is not to scale, obviously, which means since this side is 2 meters long, then the actual length, or the actual distance from the opposite end to where this force acts, (2 meters per side minus 1.25 meters from the axis of rotation, means that the answer to this question is that this block must be placed 0.75 meters from the opposite edge, or opposite end. Free body diagram, net torque equation. We figure out which torques don't cause rotation, or which forces don't cause torques. We determine each individual torque. They happen to be set equal to each other in this case. We plug in. The numbers are not all that bad. Once you practice this multiple times, writing a net torque equation will be just as easy for you as writing a net force equation. When I come back, we'll do more examples, and then we'll get into some other stuff as well. But that's the basics of torque. So right now, I'll say bye.